This is a production of Cornell University.
Welcome to the podcast of Mann Library's Chats in the Stacks book talk series. In today's talk, originally presented at Mann Library on February 25, 2010, Professor of Biological and Environmental Engineering Lars Angenent explains what a bioelectrochemical system is, gives examples of its useful application, and highlights current research in biosensors and wastewater to product conversion.
Thank you very much for inviting me to give a presentation in the library. This is the first time in my life that I feel a little bit famous, because yesterday I was sitting in the lobby here, and there was a big poster, and I was sitting next to it eating, and I almost felt embarrassed. Oh, that's me, come to the talk. So I'm going to talk about bioelectrochemical systems. I've been here at Cornell for about 1.5 years, and I'm very excited to be here, and I'm really enjoying myself, and I don't even mind the weather, so that's good. I'm going to talk about this book, but also about what bioelectrochemical systems, what they are, and how we can use them. Of course, I can't do any work without the people who work in my lab, and actually some of them are here, so about half of the audience is actually in my lab, and you can Arvind is here, and etc. So these people do all the work, and then I'm just sitting in an office these days, trying to edit a book or something like that. The reason why this book was published, because bioelectrochemical systems over the last, I would say 6-7 years, have really taken some importance in the environmental engineering research field. And it's kind of a new area, although bioelectrochemical systems are not new. The first microbial fuel cell was invented in 1910, but over the last 5-6 years, really the technology has taken a leap, and people are thinking about applications and also scale-up. And there's some issues with scale-up, but at least we're going into that direction. So we felt with 3 other editors there is a need for a book, and the outcome of that is called Bioelectrochemical Systems. The publisher is the International Water Association based in England. So the premise of these books is typically, for who or the audience who doesn't know that, is to have people in the field writing certain chapters, maybe 1-2 chapter, and asking people to contribute. And since it's an exciting new field, a lot of people actually did contribute. Sometimes it's hard to find authors for a book, and they did do it, and they actually handed in the material on time. One of the reasons it was on time, and I must say that the biggest contributor to the book, the editor, is Cornel Rabai, and he's a very aggressive, very nicely and aggressive person, so he was able to keep everybody on schedule. And you need to really have that to put a book like that together. So and I'm not going to all the chapters, but to kind of give you an idea what the chapters are in the book. The first chapter is really important. What are bioelectrochemical systems? Maybe some of you know, some of you don't, and I will try to explain to you what they are. One chapter early on is a comparison to other waste-to-energy systems, such as anaerobic digesters. Waste has been treated with anaerobic digesters, and methane is formed all over the world, and this is an energy form, so that's an alternative to what I'm talking about today. There are also enzymatic fuel cells, another technology. And then there's a couple chapters on electron transfer. How is it possible that microbes, that we all know have a non-conductive membrane, can transfer electrons from their cells through a solid electron acceptor, or a solid, in this case, electrode? What are the mechanisms of that? So there's a couple chapters on that. It's obviously very important to know. We actually contributed, the stars is where our lab contributed chapters. We did a chapter on metabolically engineered microbes who have a better ability to transfer electrons. Material choices and their effects on performance, that's important because we have electrode materials, and the quality of that material has a big impact on the performance. Again, very important part of the engineered system. Then there is a lot of very classical electrochemical techniques to measure the performance of a system, and we are incorporating some of these classical electrochemical techniques into this research. something that I'm still learning about and have a hard time with, as a matter of fact, because during my PhD I never used those techniques. So it's helpful to have chapters in a book like that for people to understand what's possible and what do you need to do this type of research. Obviously, what's very important is the applications. So some of the applications that we're thinking about is one, soil remediation. You can place electrodes in soils to help organisms clean up man-made chemicals that we need to get rid of. Sediment fuel cells, you can place electrodes in sediments and using a natural potential difference that you can then run sort of a battery about, and maybe you can run small sensors that you place in the environment powered by the sediments themselves. So that's an application. And obviously there's a need for a chapter for that. Biosensors is an application. What I'm going to talk about a little bit later on today is treatment. I'm actually an environmental engineer. Somebody treats waste or wastewater. So that's where my niche is into this, and my interest in this technology, to how to scale that up. Mathematical modeling of the bioelectrochemical system is something that's important, and there's a chapter on that. And then finally, an outlook, and I helped writing that chapter. It's obviously at the end of the book. So the chapters to which I have contributed are with stars, so there's 3 of them. One of the first things that I'm going to do today is explain to you what are bioelectrochemical systems and what different kind of configurations can you use and to, for instance, treat wastewater or for biosensors, et cetera, et cetera. So that's one of the first things that I'm going to do. What are they? And I'm going to talk about 3 different systems. One is microbial fuel cells. This is, I think, the most, in terms of the microbial aspect of bioelectrochemical system, the most famous system right now. I'm going in length in explaining how that works. Then there's another technology, microbial electrolysis cells, in which you can actually form products. So you can convert waste into a product. The top one here, you convert waste into electricity. Then there's a microbial 3-electrode cells, which I call, for this talk, actually, I never used this term before until today. I call it M3Cs, 3-electrode systems, and you can use that for biosensors, for instance. But the first thing that I want to talk about is what these 3 systems have in common is all that you have bacteria, so whole cells of bacteria that live on an electrode. And the electrode typically for us is a graphite material, so it's a solid material. So the first question is, like, how is it possible that bacteria can live on there? They can either give electrons to the solid material, then it's using the electrode as an electron acceptor, but it can also do the opposite. It can take up electrons from an electrode. So then the electrode is an electron donor. So how can organisms do that? A large group of researchers is interested in that and really understanding that to a very scientific level. So people like me, I do a mixture of very applied research and a mixture of some scientific work. Others are only interested in this aspect, the mechanisms. So what are the cellular mechanisms that are necessary to do this? And to do this at a high rate. So what are 2 of the mechanisms that people are interested in studying? One is direct electron transfer. This is, if you have an organism, this is the bacterial cell, it actually needs to touch the electrode. And the cell has several outer membrane cytochrome C proteins that form almost like a link from the inside of the cell to the outside. And there are iron and other conductive molecules. Iron is part of these heme groups in these proteins, making a direct conductive link between the cell, inside of the cell, and the outside. Okay, so there's different proteins that are involved in that. Cells have to touch the electrode. Okay. Another mechanism that's of interest is by using soluble electron mediators or electron shuttles, the bacterium does not have to touch the electrode. It just goes, there's a chemical, a compound that's excreted by an organism, and it's being oxidized and reduced to transfer electrons. So in this way, the cell can actually have a distance away from the electrode, and you can have, sometimes it could be more efficient. So these are 2 mechanisms. There's other mechanisms that are around, but I'm not going into detail of that. These are the most popular mechanisms that people talk about. All right, so that said, that was important for us to understand that there's only bacterial cells involved in these bioelectrochemical systems. And in this case, I'm depicting a classical microbial fuel cell where the bacteria are on, and in this case, touching the electrode material. So your bacteria, they grow on the electrode here, and the electrode is the electron acceptor. Then the electron donor would be organic material that is part of the wastewater, for instance, acetate. That would be the electron donor here. The way this works is that bacteria transfer electrons to the electrode. The only way that these electrons naturally can move from an anode to the cathode, so the left side here, I depict a chamber that's called the anode chamber. There's a membrane in between the two chambers. On the right is the cathode chamber. This setup is very similar to a hydrogen fuel cell, and you've all heard about a hydrogen fuel cell. Maybe you haven't thought about how it works. So there is some similarities. There are also some differences. Okay? But what we have here, we have a solution. In here, the bacteria live in the solution. They grow, and they transfer electrons to the electrode. Electrons then naturally move from the left to the right through an external circuit. There's a resistor here. This could be a fan or a lamp. So that's how you actually create electric power. And the electrons move here, and then they react with a proton and oxygen. And in the end, you will actually form hydroxide molecules. So actually, the pH will go up in a microbial fuel cell here. The reason for that is because typically when you have a hydrogen fuel cell, actually what moves from the left to the right through the membrane are protons. And this is necessary to keep electroneutrality conditions because I'm moving a lot of electrons, so negative charged entities from the left to the right. So I need to do the same thing with positive entities, otherwise I'm depleting it of a charge, and that's just not possible because you will have immediately a resistance in the system and the system will stop. So you have to have movement of positive, in this positive like protons in the hydrogen fuel cell. But in our case, the pH to grow these organisms are at pH 7. So you know from chemistry that the concentration of protons is extremely low. 10 to the minus 7, right? Remember that from chemistry? So that said, the concentration of cations like sodium in wastewater and in nutrients is so much higher that protons are not moving, but what ends up moving is cations. It took about a couple years for us to realize that in the field. But now this is pretty much accepted. So since the cations are moving, not the protons, to get this reaction done, you steal a proton from water and you produce hydroxide molecules, and the pH will go up. And that's a problem actually for scale-up. So we're working on how to solve that. All right, so we're having electrons moving from the left to right, cations moving from the left to right to maintain electroneutrality. In this case, it's a classical fuel cell. We use platinum, see here, platinum on the cathode to make this reaction possible. And what I want to show you here to make sure that I explain this right to you, and to show you what the difference is between microbial fuel cells and what I talk later about as microbial electrolysis cells, is the fact that this is a natural occurrence. Because I'm having a reduced substrate, in this case maybe acetate, so reduced substrate that's going to be oxidized. So I have a potential in my system of about, in the anode, of about minus 0.2 volts, give and take. So since I have that, and on the cathode side I add oxygen, and that potential is much higher. When you include the losses in the system, maybe you say you have about 0.3 volts there. That's the potential on the cathode. So you can see that this one is more positive. The electrons are actually naturally moving to the right, and you can get an electric current. And if you then put a resistor on there, you make electricity, you have electric power. But this is natural, and you don't really do anything else. Besides putting a resistor on there, and you get electricity out. Is that clear to everybody? So this is a natural occurrence. You don't have to do anything to get that. All right. Are there any questions thus far? Because this is important. If you don't get it right now, then we're going to lose you pretty fast. So this is a microbial fuel cell. There's a lot of different configurations, but this is the classical way. I also want to show you that obviously when I have a wastewater treatment plant and I start, these systems are going to be large because the kinetic rates are not so good. I can't use platinum. Platinum is extremely expensive, so I can't have very large electrode materials with a lot of platinum on there, right? So that's obviously a problem that we need to face. But luckily, it turns out that, and I had already given that away, that bacteria can also use a solid material as an electron donor. Okay, not only acceptor, also electron donor. So rather than taking acetate, it can use a solid material. But you obviously have to provide an electron acceptor, which could be, in this case, the terminal electron acceptor oxygen. So then you have a truly microbial system, both microbes on the anode and the cathode. I only need a cheap carbon material, like graphite material, that I need to find somewhere. We like to use carbon fiber, the same material that you make tennis rackets and cars and stuff like that. So that's a material that we use. It's relatively cheap. And then we need to grow things on the both anode and cathode. Obviously, there's a lot of problems with scale up and kinetic rates, etc. But I'm not going to talk about the problems. I'm going to talk about how it works here. All right, so, but for us, everything is the same, as you can tell. It's the same system, and I don't need to spend a lot of money on my catalyst. Especially in the beginning, when we started doing this research, we used something that mimics platinum or the cathode, which is a terminal electron acceptor. In this case, that is ferrocyanide. And that's nice, because you don't have to worry about the cathode so much. And you don't need oxygen. It can be an anaerobic system, but you use that up. You use up that ferrocyanide, and you need to keep using that and add that. So it's a non-sustainable system, would never work at the full scale, but it's great for lab research. All right, so this was our first MFC that we built in the lab. That's based on an H-type design and looks very similar to that picture that I just showed you. I have bacteria on the anode, and then I have ferrocyanide in the cathode. There is a membrane, in this case a cation exchange membrane between the anode compartment and the cathode compartment. And you now know how it works. The substrate gets oxidized in here. The electrons move from the left to the right. I have my ferrocyanide, that's a terminal electron acceptor, and my electrodes in this case were carbon paper at that time. It's a classical H-type MFC, very old, about 100 years old. And that's what we start using it with. But you can see here, one thing that we need is some mixing. So we have this mixer with a magnetic mixer. And obviously, you can tell I can give it you away. We put more energy into this mixing than what we got out. So this is not a very sustainable system, obviously. So these H-type MFCs, I think they're excellent tools for research. We're still using them. But it requires mechanical mixing, which costs energy. That's not going to work. It also has a very small electrode surface area. And our kinetic rates are low because we use bacteria rather than in a hydrogen fuel cell use hydrogen gas. Kinetic rates are much higher with a metal, there's a platinum catalyst. And therefore, we need to increase the surface area by a lot more. So this would not be practical for wastewater. So what we're trying to work with is think about it as a wastewater treatment system. So do something different. Make it continuously fed, obviously, because wastewater, we always go to the bathroom. It's not that we're going to stop doing that for a very long time. So it's a continuous process. The other thing we did was we had a three-dimensional electrode. And what we did, we used granular activated carbon. It's a cheap material, high in carbon, pretty conductive. And if you use a bed of these granules that are about this size, and you pack them in there, they're conductive. It becomes one big conductive material. You stick in an electron rod, and you have a conductive material. And you can flow the wastewater through it. The bacteria grow on the outside of the particles. Right, and they're doing the same thing. They are using this material as an electron acceptor, right? And my wastewater, again, is electron donor. We use our cation exchange membrane. That's a membrane material. And we rolled it up in a U-tube. We put granular activated carbon in there as well, inside here. Stick another rod in there. And now we have two conductive electrodes with a membrane in between and a circuit. Electric circuit. And so we start feeding it. You don't even have to feed that long before you get the right organisms to grow, and they start producing a current. What we obtained was a maximum current of 29 watts per cubic meter. So you know how a cubic meter is, and I'm producing 29 watts. That's not that great, but it's also not nothing, right? So there is some hope maybe in the future to use this. the internal resistance was 17 ohm. That's way too large. And one of the reasons it's large is because these electrode materials, like for instance this particle here, this anode is just too far away from the other electrode. And since I told you that these cations have to move, you have a high resistance of this almost like a diffusion-like way that these ions have to move, and it's not very efficient. So you have to improve that. All right, you can do this at home. You have all heard about the potato experiment, right? And so you could, and a lot of high school students right now design all kinds of different fuel cells, so you can do this at home. You can make it. I can give you a little electronic, little bit of membrane, et cetera, and you find some carbon material. You can do it at home. And the one thing that you would do then to see how much your maximal power is you calculate a power curve. And that power curve is given here. This almost like mountain thing. So what I'm depicting here in this figure is I have my measured potential. So you go to Radio Shack and you buy yourself a potentiometer. You've all seen them. Sometimes they're yellow and you can read off the screen. So that's a little investment that you have to do, or maybe you even have one at home. The other thing you need to do is buy a lot of these small resistors at Radio Shack. You can get them from 10,000 ohms to almost 0 ohms. So you have to buy a bunch of those, okay? So now you have your two electrodes, and now you're going to have your wire in between, and you put these resistors between the two electrodes, and you start reading off your potentiometer. That's all you need to do, and then some calculations. Okay, so we have our measured potential here. The first thing you do is you actually have your two electrodes, and you don't put anything in between. So there is open potential. There's nothing. There's no flow of electrons possible because there's no wire connecting the two electrodes. And what you're going to read is you're going to read an open potential number, which is, I told you this was a natural thing that occurs because you have a potential difference based on your anaerobic environment in your anode and your oxygen in your cathode. So let's say that's about 0.8 volts or 0.7 volts. What you're going to do now is adding these resistors, and you start at a very high resistance, maybe 10,000 ohms, and you measured it for a couple minutes, and you put another resistor in that's a little bit lower. And what you will read off is this curve here, which is called the polarization curve. Okay? So you have your measured potential, you have your current that you measure as well, and this is actually converted to my anode volume. And what I can calculate that with Ohm's law is my volumetric power, and basically what I calculate then is this curve here, a simple calculation. And what you report in a paper, or what you report as a high school student, is this number here, the maximum power that you can obtain. And this maximum power, in this case for our system, was at an external resistor, so this thing here that we have in between the electrodes, of about 20 ohms. That's our external resistor, and that's the maximum power that we got. That also often means that the internal resistance of the system is very similar to that number. So it's about 20 ohms or internal resistance. Does that make sense? So this is what you want to be the highest, obviously. So who's going to do this at home? Maybe. I got one person here who maybe is going to do it. So it's actually a pretty simple thing to do. This is a system that we built in the lab. It's about a 10-liter system, and we were using real brewery wastewater. And instead of putting that Radio Shack resistor, we bought a small fan and put that in there. And you can see that you can have a little fan running. And this is powered by microbes. Obviously, we have a lot of pumps around that probably take up more energy than we're putting in, but we're not talking about that today, all right? But it works. All right. Now we're going to the second example of a bioelectrochemical system, which is called microbial electrolysis cells. And what engineers love to do little back-of-the-envelope calculations. What we calculated, the amount of electricity that we can possibly get with a wastewater treatment situation. And we found out that it wasn't that bad, the amount of electricity that you get. But in terms of economical value, electricity turns out to be extremely cheap. And we would invest hundreds of thousands of dollars and only get a couple $1,000 worth of electricity on a yearly basis. So it didn't make any sense to continue that work because it would never be economical, because you can imagine that it's a large system, a lot of electrodes, wiring. It's going to be costly to build. So you need to have some economic incentive for anybody to do this. Obviously, you have your wastewater treatment, and we'll talk about it in a little bit. So there's an advantage of doing it that way. But what people then thought is, well, electrochemical systems, you don't need to make electricity, but you can actually make other products. And that would be a higher value compared to electricity. And that is done in the microbial electrolysis cells. Everything is exactly the same, except for that we do not put a resistor in here, but we actually add a power source here to add a little bit of power to the system. Okay? So as I showed you before, this electropotential figure here, and I showed you acetate, which is what's minus 0.2 volts, and I said that oxygen was about 0.3, and I have a natural potential difference that makes the system run. If you want to make a product, in this case, what I'm showing here is hydrogen gas. This is in anaerobic conditions. It's a reduced environment again, right? So what I'm having here is I'm having actually a more negative potential, and this would never run. It cannot run by itself. So what we need to do is we need to lift up this potential to a certain level that hydrogen will start forming. That will cost me electricity. I have to put electricity into the system to make that work. You can say, well, why are you doing that? Isn't that a little bit like crazy because I'm just using electricity to make hydrogen? It's not entirely crazy, and the reason for that is because first, we're still treating wastewater in our anode, and we need to get rid of our wastewater. Second, there is a natural potential difference already here. So if you want to make hydrogen with this anode, it will cost you about 1.2 to 1.5 volts that you need to put into the system to do, as you all know, water electrolysis to make hydrogen. In this case, we probably have to put in only about 0.7 volts or something artificially. So we don't have to put as much energy in to get hydrogen out. So that is the premise of a microbial electrolysis cells. You can make hydrogen, you can make a lot of other methane. People are thinking about a lot of things. Recently, very recently, people are getting excited about CO2 reduction. So you can also reduce CO2 on the cathode and produce a product. And that's exciting for carbon sequestration. So people are moving towards that. The problem is always, can we scale this up? How fast can we move this into a real life situation? All right? So any questions on the microbial electrolysis cell? The difference is I'm putting some electricity, some energy in to make a product. I can also run this as a microbial 3-electrode cell. In this case, what I do is I have everything the same, but I'm adding a reference electrode close to my anode electrode. And what I'm basically doing is locking this, or setting this potential at a certain number, while I then add the rest. On top of that, I'm adding it to the cathode, this potential difference between the anode and the cathode to make, in this case, hydrogen. Okay? So this is a 3-electrode potential. The difference between that is here, this is a 2-electrode system. If I increase this hydrogen, most likely this potential in here will go up a little bit. It's not set at a certain number. Here I'm setting that potential. And I can use this easily as a biosensor. And we're doing that in a system that looks a little bit different because as you see here, I still have, in this case I want to make hydrogen, so I still want my cathode, but I don't need that. For a 3-electrode system, I can do everything into one vessel. So I don't at all need to use the cathode, and I'm just simply setting my potential however I want it of this, what I would now call working electrode, where we have our organism grow. And so this is ideal for research. I don't have to worry about membranes. I don't have to worry about a cathode. I'm just buying a potentiostat. They're expensive, but you can deal with that. And set a potential and do research at something that's much more controllable. But I also can use it as a biosensor. And we have a project that we put these systems in soil in Alaska to measure microbes that are doing this transfer of electrons to a solid material. So it becomes easy for us to do research. So we have a bunch of these single vessel system in our lab, and then we can do a lot of research. I'm not going into that research, But I'm just showing we can do gene expression of some of these organisms that are involved in electron transfer. Now everything that's red is expressed at high levels. For instance, these outer membrane cytochrome proteins that I was talking about initially that do the transfer. So we can do research on these control systems. All right. Then we're coming back to the book. Now you can breathe again, hopefully for a little bit. But the book, my role in chapter 19, with several authors in my lab, is to see if you have a wastewater treatment system and you have this technology, and let's say that I can scale it up, where in the system am I going to place this? Okay? So we came up with a bunch of different ideas, and we decided to do that kind of in a graphical way, so we made a figure. And what I'm going to do is I'm going through to not to all of them, but to several of these examples, and you can see then there's a figure that belongs to that example. And we had about A to G. How many is that? 1, 2, 3, 4, 5, 6, 7. So I'm only going to go through a couple here. But before I do that, I first want to show you how your wastewater in the morning, you go to the bathroom, is treated. And some of you know this, some of you don't. And this is done in the United States mostly with activated sludge systems. The wastewater comes in. It first goes into a primary clarifier where larger materials get settled out, because if you can easily remove it by just settling, you don't need to further treat it. And that is an overflow of the wastewater, so everything that's still soluble goes to an aeration basin. This process is called activated sludge, and where it's basically the soluble material is converted into bacterial cells. Here, the electron acceptor is oxygen. Okay? So it's an aerated system. If I have a big activated sludge tank, let's say this is my aerated basin, I'm going to put a lot of discs on the floor that distribute this oxygen very nicely. You make very small little bubbles to get as much oxygen transferred from the gas phase into the liquid phase. But I need big blowers, big pumps, to put a lot of that air into the system, and that's energy intensive. So right now, if you make more wastewater, that will cost the society more energy to convert. And this is not little. So that happens in this aeration base. What happens next is, now I have converted all the soluble waste into cells. They go to a secondary clarifier. They settle out. So this is biomass settled out. And the material is now converted. There's not as much soluble material. This comes out over the wire and goes into your river or your lake. Okay, so it's clean now. This biomass is a problem. I created a lot of biomass. I need to do something with that. And you go to the local, next to the farmer's market, there's the wastewater treatment plant. There's a couple big tanks that are anaerobic digesters. They take this material and they move it into this digester to remove about 50% of the cell material, and you convert that into methane. So two things are happening. One, I need to put in a bunch of energy to aerate these tanks. I get some of that energy back because I'm producing methane, and I can run a generator or something like that. But unfortunately, I need to put in more energy here than I get back. So that's obviously something that's not sustainable. All right, so now we're going to talk about energy use. About 2% of all US electricity consumption goes to wastewater treatment. So that's quite a lot, I think. 50% of that goes to aeration. So 1% of all the consumption of electricity goes to aerating our wastewater. And that's maybe not sustainable. So that's why we're interested into these MFCs. So now you can think about where we're going to place these bioelectrical systems, or these microbial fuel cells, for instance. We're going to do that. We can first think of it's a standalone technology, and it just takes over the entire process. I don't need digesters, et cetera, et cetera. I'm just the whole thing converted into microbial fuel cells. Complex wastewater converted into current. It works at lower temperatures than anaerobic digestion. That was the competitor to this technology. You would place it in the beginning. The thinking is because the concentrations of organic waste are highest at the beginning of the system. But, okay, this is dangerous when people say but. Obviously, this is not going to work. And why not? First of all, the organic concentration coming out of the anode in here the organic concentration is still too high, so you need to do a post-treatment. You need to do something else with it. You cannot just put it into the river or the lake. So you still need an activated sludge process. The other thing is that you almost have no nutrient removal, and for instance, in Ithaca, they have to remove both nitrogen from the wastewater, but also phosphorus. So a fuel cell wouldn't do that at all, and you need subsequent treatment. Okay, so it wasn't as simple as what we hoped for. The other thing that's really important is we measure our efficiency. You know, engineers obviously always come up with an efficiency measurement. Our efficiency of the bioelectrochemical system as a number that we call Columbic Efficiency. It's basically how many electrons that are in the electron donor, which is the wastewater, will I actually get out of my system? What can I get as electric power? And if you use real wastewater, this Columbic Efficiency is very low, from 20 to 5%. So that's not very efficient. I still have 80% that I'm not really using in terms of energy production. If I use acids, however, for instance, if I use acetate, somebody got 100%. That's obviously not at steady state condition because you can never have 100%. This would be great. If this was really 100%, we would all be done, right? We have a complete conversion, but that's not the case. But it's much higher, as you can see. Let's take an average or something like that. Much higher efficiencies. So one thing we could do, what we have to do, real wastewater is not working that well in microbial fuel cells. So one thing we could do is place what they call a pre-acidification tank. This is an anaerobic fermenter in front of your microbial fuel cell. And what it does is convert some of this complex material into acids. And now I can treat it much better into my microbial fuel cell. And so this is a higher Columbic efficiency is what we need. So this is one way of doing that. The other thing we can do is instead of placing it at the front, we are doing it at the end. Because we have this digester. I explained to you that we have an activated sludge system, and we have a digester. Now, if we make this a thermophilic anaerobic digester, one of the disadvantages actually of thermophilic anaerobic digester is that you create a lot of these acids that come out of the digester. And what to do with them next has always been a problem. So now, but in the fuel cell, that's what we really want. So what we could do is put the fuel cell after the thermophilic anaerobic digester. Right? So in that way, the concentrations of this substrate are actually, this is in a sense, after this secondary clarifier, this is a much higher concentrated material. So our energy density is much higher in there as well. And you can place it at the end of the treatment plant. Another thing that you can do, and this is by using a biocathode. Remember I told you that I didn't want to use platinum anymore, but we can put bacteria on the cathode. So what I can do is in the anode, you can place this in any situation, in any location of the wastewater treatment plant. Here I'm treating wastewater. But in the cathode I have organisms growing that can actually convert nitrate, that can actually convert ammonia into nitrate. Okay? So we can get rid of nitrogen in this system. And that's what we need. We need nutrient removal. So in this case, you would have, on the anode, you would have bacterial biomass, and on the cathode as well, you have this biocathode. So that's one other way of maybe dealing with wastewater. And then we come to the microbial electrolysis cells that I had mentioned to you. These were cells where I add some electricity, some power, to produce a product. Okay? And I need some products in my wastewater treatment plant anyway. So there's a couple examples that you can do is, I can, and I mentioned that to you before, I can make hydrogen in the cathode. So I'm treating wastewater in the anode, but I'm producing a product in the cathode by putting a little bit of potential on there. And I'm making hydrogen. Hydrogen is used as anyway at the plant right now for autotrophic denitrification. You would have to buy this to use it at the wastewater treatment plant. But in a sense, I can make this from wastewater. So I can integrate that within the plant. The other thing we can do is produce hydrogen peroxide. Again, you do this on the cathode by adding a little bit to get the kinetic rates. In this case, the kinetic rates up, you can add hydrogen peroxide, and you can make that. This is also something that is being used at the wastewater treatment plant. Actually, the wastewater treatment plant here buys hydrogen peroxide that comes from non-sustainable sources, right? But we can make this ourselves. One thing you can do with it is adding some iron to and plus hydrogen peroxide, and it creates a chemical reaction that's called a Fenton's reaction. Very strong oxidant, and that can reduce very potent man-made pollutants. And it's a very strong oxidant, so people like to use it in wastewater treatment plant. One example is to remove dyes. Some dyes are very hard to remove from a wastewater treatment plant, but with this Fenton reaction you can do that. So I can make this sustainably at the wastewater treatment plant. All right, so this is the last slide of the talk. I think it's going to be very hard to scale this up into a wastewater treatment plant, and we need several breakthroughs. If we are able to do it, then we need to take advantages of almost all the things that I mentioned. We need to be able to remove wastewater, and we need to produce some valuable product. I think it could be a very good polishing step for that thermophilic digester that I mentioned to you, so I would never put it in front of the plant. You really need a much higher concentrated wastewater than the domestic wastewater that we produce. We need breakthroughs before you can actually successfully scale this up. And I think the latest application that I don't even know if it's mentioned in the book is what people are looking at is to reduce CO2 in the cathode. To also, on top of everything else, to also be able to sequester carbon dioxide. And carbon dioxide is another compound that's often produced at a wastewater treatment plant. So we need everything to make this successful. That's my talk, and if you have any questions, we have 15 minutes left. Thank you.
I just had a quick question. For the pre-acidification, that would add acid to the process. So would there be any other side effects to adding these acids to the wastewater treatment plant?
Yes, one side effect obviously that you're going to drop your pH. And some wastewaters have high alkalinity and it's not so much a problem. Other wastewaters don't have that, and you may have to externally add maybe magnesium hydroxide or something, a chemical, to bring the pH up. On the other hand, and I didn't show you that figure, but we can make peroxide, no, not the peroxide, I mentioned the peroxide, but I can make this OH minus in my cathode. So in that way you can integrate it all to prevent that from happening. That was one slide that's given in the book, but I didn't want to tell it to you because I thought maybe it adds a level of complexity. So indeed, you need some base, in a sense, to bring the pH back up.
Hi, I had a question about applications. Have people looked into using these type of systems as a small distributable system for maybe treating waste in remote regions or places like ski resorts? I know people have looked into using smaller systems where scalability may not be so much of an issue.
People have thought about it. One example is there's a company that came out of MIT, I think, and they went into a very simple system. They have kind of a bucket system, so it's not bigger than the bucket, and they have, in the bottom part, they just put a lot of cow dung or something like easily degradable and very energy rich, as you can imagine. You put in an electrode material, some cheap carbon cloth maybe, and then you have some sand in the middle, and on the top, you just put liquid, like just water, and maybe you add some salts to that, because conductivity is always good. And then there's a natural amount of oxygen coming in the top. And obviously, it's a microbial fuel cell because you generate this natural potential difference between the two. And maybe if you have several of these buckets, you can produce enough current or enough electric power to power cell phones or something. So like in the developing countries where people have cell phones but no electric power, this could be a very easy way to power cell phones. So that's just one example. That's the only company that I know that I can see has done something that's successful. In terms of sediment fuel cells, so the sediment fuel cells maybe in the sediments of the ocean, etc., people have built pretty large systems to power sensors that they put into the bottom of the ocean. Why that's an advantage is because your sediment always have organic material, so it's a battery that never runs out of fuel. If you do the same thing and you put a battery down in the ocean, after a year you have to go back and take this normal, lithium battery or whatever you want to use back up. So in this way, that's another an example where something successful has been made from this technology. Other people have tried to scale up. There are companies around, and I have not seen a successful implementation of the technology. And I think we're a little bit early for that. But on the other hand, I'm also excited about it. So maybe 3 years, maybe 2, 3 years, 4, 5, 6, 7, who knows?
Do you know anything about the differences in the microbes and the communities in these microbial fuel cells versus, say, in aeration basins? Are they the same species, or has anyone studied this?
People have used inocula from these aerated tanks, but you very quickly see that the community changes, and it drastically changes. So these organisms are obviously around in the activated sludge, which is a very diverse community, but then they get enriched onto the electrode. So you see a very large change in the community, and we've done experiments like that. So very drastically. And there are certain groups of organisms that then are the biggest player in terms of the. So you have a mixed community. I have, for instance, a species that, in our case, what we found when we did that experiment, we found Geobacter. That's a species that's known to do direct electron transfer, and it's very good at it. It's a very popular organism that does that. So then the rest of the community is only making these acids. So you have a complex waste, like maybe I'm putting sucrose in my reactor. I have a lot of fermenters in the biofilm, and the only thing they really do is making this acetate for Geobacter. So that Geobacter then can transfer these electrons to the electrode.
Of the different products that you mentioned, which do you think is the most promising, or the most, of potentially biggest impact?
We are working with hydrogen peroxide. There was a paper already came out on hydrogen peroxide, not from our lab, from a different lab. So we're really excited about hydrogen peroxide. There's a life cycle assessment done, not by us, by others, that have found that because it's a sustainable system of making hydrogen peroxide rather than a non-sustainable way of doing that it's a real advantage system. So hydrogen peroxide, I would think, is something that's really lucrative. If you can, on the other hand, if you can reduce CO2 into a product, whatever that may be, and you are able to sequester CO2, then you really got a winner, and also that for economical reasons. But I think that has up till now been somewhat of a problem. We're working on that to make a product. But I'm not going to tell you which product that is.
If you get to the point where you have something that you would want to try to scale up, how do you work to experiment on systems that are public systems? Most wastewater treatment are municipal systems. Or how do you go from the lab to the application?
It's very easy to get wastewater. No, people just want to give it to you for whatever reason, and so we work with I had the little movie that we had was from wastewater from a brewery, and we work very close with Anode Chamber, and we have a nice working relationship with people there. And again, they don't mind giving wastewater, so we just ship buckets of wastewater, keep them in the fridge that it doesn't ferment, and then we feed that into the. That case was a 10-liter reactor. We also learned from that we, in a sense, we scaled up a little bit. We had little devices in our lab and went to 10-liter. That was too early. That our internal resistance are still too high, our power is too low. And so now, rather than doing that, we are staying at a smaller scale and really trying to work with materials. So it becomes more of a material science issue. And now we're trying different electrodes, But the systems itself, you can come to a lab and then they're about this size. So I think it's, again, a little too early for the scale up before we need to figure some things out. Another question.
Sorry.
Not as good.
Drawing on your question, when the process is more or less confirmed and in the lab, besides having a book, how would the advertisement or the promotion of the idea ultimately reach, I guess, the local governments and ultimately incorporating into modern municipal wastewater treatment plants?
One of the reasons I think this country is doing well in the United States is because it's based on capitalism. If you develop a system that's truly economical, it's very easy to get people on board and to try it. And one of the things that I think this country is very good at is having money around that you can start up a company. If you have a good idea, it seems that it's okay. It's relatively easy to get money. Another thing that's different from maybe other places is that here there's room for failure. Obviously, when you start something new, there's going to be failure. And you can have several startups. I know people with 3, 4 startups. The first 3 failed, but they still were able to get more money. So that's one thing I think that's good about this country, that people are willing to try something new. So if you have a winner, if something does make sense, and you can show that you can scale this up, it's very easy to obtain money to take the next step. So I think that that's something that's a good thing, obviously, because we do need to transfer the way we treat wastewater, because right now it's non-sustainable.
Okay, well, if there are no other questions, I'd like to say thank you. Really interesting talk, and thank you all for coming today.
Thank you.
This has been a production of Cornell University. On the web at cornell.edu.